In the next 15 or 20 minutes, what I'd like to do is bring you up to date on our thinking about what we call Earth virtualization engines. As Thomas mentioned, we've been discussing these ideas for a period of months and somewhat intensively over the last 6 months. And our thoughts have evolved. So a lot of you might have a picture in your mind of what we're thinking about. But as the world has changed and as we've met and discussed, new ideas have emerged. And we haven't settled completely on what these ideas are, but I'm going to share with you what the current state of our thinking is. And the purpose of this meeting actually here is to involve a larger community to see if the direction of our thinking is correct and to see if we can come up with a common understanding of the opportunity. So this is my take on the sort of dominant ideas that came out of these intensive discussions over the last 6 months. And it's really about putting the world in people's hands and engaging them in imagining and interacting with their future. That's, I think, in a phrase, what Eve is about. And if you think about it, we have many institutions that deal with climate change. And a lot of them originate out of a time in the past when we were dealing with very different sorts of questions. So just for fun, I went to the New York Times in the year 92, 93, right after the Rio conference, where the UNFCCC was brought together. And this is what people were talking about. You know, there was this theory of global warming. The issue is, do we see it? Do we see it not? Is the theory right? Is it wrong? What's the evidence of the past? But what climate science was tasked to do at that time was to resolve knowledge disputes. People had different ideas about what was happening, and we had to weigh in as academics and say, what do we know? I think it was Deborah Roberts, you can correct me if I'm wrong, who said, now the question is, what do we do? And if you think about that, that's a really profound change from a knowledge claim or a dispute about knowledge claims to saying, what do we do? Climate change is here. And because it took so long for people to realize that fact, climate change isn't here, it's here, 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 here. It's everywhere, it's every day. This is a kind of a week of headlines in the New York Times. The previous one was a year of headlines, or 2 years of headlines in the New York Times. So as people accept climate change, it's become responsible for everything. And it's led to speculation about everything. And so what's new is that climate change has become a practical problem. And suddenly everyone needs information about everything, everywhere. And that's completely different than what it was 30 years ago. And it demands a different type of response. And this is what we're trying scientifically to envision. How can we do something? So I kind of like this way of thinking about it lately. When you think about the old problem of resolving knowledge disputes, we use these information science paradigms, and some people call them these DIKW, sometimes there's wisdom on the top diagrams, where you have this idea that you have data, you have some empiricism about the world, and you'd like to curate that into information, and out of the information you'd like to draw knowledge and maybe even wisdom. And it's really a flow upwards from lots of data to less information to even less knowledge. And in a way, this flow of information really shaped how we addressed the old problem. Is the world warming? Are humans responsible? Does it matter? It's not so good for addressing the new problem, because if somebody needs to change their water resources, if they build a dam, you can't say, wait, we're going to have a report coming out in a few years, and we'll ask the academics to weigh in. That doesn't work, but it's in many ways what we're still doing. There's wonderful exceptions, of course, but they just prove the rule. So the situation has changed, but two other things have changed. One is that HPC, computing, like the Satoshi Matsuoka over there, runs this fantastic computer, which is so far beyond what we typically use for climate science. And it allows us to do something really fundamental. It allows us to take knowledge and create data. So what's the knowledge? The knowledge are the laws, the physical equations, our understanding of the system. And through that, we can simulate and create a sort of pseudo-empiricism, new sorts of data. So we can go from knowledge to data. But if we do that, don't we want to do that as good as possible, as much as possible? So this is one of the realities we were dealing with, that we can create data from knowledge. So that's one change, the ability of computing. Another, and this is also a very important one, and it's happened very recently, is that artificial intelligence, machine learning, makes it possible to extract information from data. And it allows that to happen in ways that were inconceivable before. So if you think about that knowledge pyramid, how you went from data to information to knowledge, it's completely changed. So not only do we not need the pyramid, we need to turn it upside down. We have two new things going on. One is the ability to go from knowledge to data in unprecedented ways. And the other is going from data to information. And it's the information, actually, that we need. Of course, we'd like knowledge, but we need information. And so knowledge is just part of the pyramid now. And we can put this all in motion. But if we wanted to do it, it doesn't really make sense for individual institutions. Just think about that. If you're responding to users, you have an institution that has a mandate. It wants to do one thing. So it doesn't want to create a giant system to do everything if it's just tasked with one thing. And even if it did, tasking the world's largest computers to solve the world's largest problems isn't something that you can get every institution to do. It demands people coming together. And the same thing if we want to turn data into information. It's not something that you want each institution will do that all the time. It's something that you want to open up in a way that can involve everyone, but that not everyone does it in a redundant sort of way. So these are the three changes, and I want to speak about one of them, or two of them, in a little bit more detail. So the first is HPC, high performance computing, and its ability to transform the way we see our world. So this picture, some of you know, people who've heard me talk before know it. It's the blue marble. It might be the most important photograph ever taken in the history of humankind. It was taken in December 1972 as the Apollo spacecraft, the last one, Apollo 17, was headed to the moon for the last time. And people look back and they snap this photo. People credit this photo with changing the way people looked at the world and helping people see the world as a whole. So sometimes when people see this, they can get shivers because never before had people seen the world as one. And in the early 70s, when people saw this photo, it's credited with reshaping human consciousness and giving birth to the modern environmental movement. It's technology. We needed a rocket to get there. We needed a camera, and we needed the wisdom to look back and share that with each other. And the amazing thing is, when we realized in my institute that this was coming together, we worked with some people at the Computing Center, Daniel Krocke, he's somewhere over here, somewhere over there. We had the idea, maybe we could simulate this. So we took the little bits of data that existed at that time. Remember, this was before satellites, and we said, let's throw it in the model and see what happens. And this is what came out. So, in the past, we could look at the world, and now, just on a whim, we could simulate it. And not only can we look at the world, but we can put it in motion. So we can look at places where the astronauts weren't focusing on. We can watch the clouds move, but we can do so much more. This is a model that's coupled. It's an atmosphere ocean model. We can couple it to the biogeochemistry, the aerosol. We look at ocean heights. We look at ocean eddies. We can zoom in and see all the things that were happening in that world, sort of. Because it's not exact. Winds and clouds, how they interact at different scales. This is wind speeds, and you see this global extent of fine-scale features. You zoom in and you zoom out. You see how the winds interact with the clouds. And you can go anywhere on the world and look with really local granularity globally. So it's a snapshot of what we can do. And today, we could run this model coupled on Satoshi Matsuoka's machine, if it was ours, we could run decades of this simulation, and we could do it 3- or 4-fold. And so the question is, why aren't we doing that? If climate change is the most important problem in the world, why aren't we using the biggest machines in the world to help us solve it? Why aren't we looking at local granularity globally together to try to understand the changes that we're facing? And that's one of the driving factors. And one reason we aren't doing that isn't just because we're lazy and we don't have the resources. One reason is very practical. It's that how do you do it? You know, the amount of data is just fantastic. So that leads us to this thing which we've always talked about, which is this, I call it the Borges paradox. And I'm sorry to the Argentinians in the audience for the Spanish speakers for completely mutilating the pronunciation. But Jorge Luis Borges was an Argentinian author from the middle part of the last century. And he wrote this essay, so maybe I'll just let you read it. I think you can read it from the back, and I'll read it in my head, and then... I like that. And still today, there are tattered ruins of that map, inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. So we have this idea that we can create, let's think of this fantastic maps of future worlds that we can help use to guide action, that we can do this together. But the problem is, trying to unfold this map overwhelms us, because it's bigger than the space that we live in. So what do we do? And this was always a challenge. We could run these computations, but we couldn't really analyze them. And this is where AI comes in, because what it does is it allows us here, they had to unfold their maps in physical space. What we can do now is we can unfold our maps in digital space. We open a new dimension. And in that dimension, we can use machine learning to ask us what the information content of the maps are. So we're using machine learning in the most powerful of ways as an interpolator of data that exists in that digital space. We're not asking it to make up new projections. We're asking to tell us what lies in the space of the existing projections. And by doing that, it allows us to access enormous amounts of data in ways that we couldn't possibly do without AI. So this is that third element in the changing landscape, is how AI solves for us Borges's paradox. It allows us to go in and figure out what the projections or what the models are saying. And here's the master of AI, Jensen Huang, who is from NVIDIA, just walked in, so it's a perfect moment. So welcome, Jensen. So what this brings out is these 3 points that we have, is the world has changed in 3 fundamental ways. Climate change has become tangible, so we should really understand what that means. And it's shifted the onus, we of course want to understand, but it's shifted the onus from understanding to knowing what to do to guide action. And this is creating needs for information that we cannot scale existing institutions to meet. We have to do something new. Our calculation. HPC has reached a scale that allows us to create data we need from things we know. So we can go from knowledge to data. But these technologies are out of reach of even the most elite institutions. You know, we get a little bit of time to do a showcase on this machine or that machine. But we're not dedicating the resources to the most important problems. And third, ML is removing barriers to our efforts to extract information from data. So it could be observations, it could be the simulations of the future. But we lack an infrastructure that allows us to do that easily. Imagine if the data was all laid out and you come from, my example, Namibia, and you want to look at a climate projection. It's one calculation to say I've been involved in creating that projection and we know how to train ML to tell us what the data says. And it's another calculation entirely to say I have to build up my own climate modeling center to do everything from scratch. So let's do the things together that belong together and do the things separately that make sense to do separately. Thanks to, and another point is, a lot of this is going on. So sometimes when we say this, people say, well, that's not new. WCRP is doing this. They have this program. Or, oh, WMO has this program. And of course, of course, a lot of this is going on. And that's why we know how to do it. But what's not going on is bringing this together in new institutions where we work together to inform the world as well as possible about the changes that are coming forth. And if we begin to do this anew in new institutions with Eve, we have a chance to actually do it together. So if you look at the existing climate system right now, you see a huge divergence. People don't like to talk about this, but rich countries are developing their own climate information systems. Switzerland has Switzerland 2025. They're downscaling to kilometers. The United States is downscaling to kilometers. The British, they do their own downscaling. Some people do it a little bit for the country of choice. The world is developing on a national level unprecedented abilities, but the most vulnerable people are actually being left behind. And so why are we doing this? Why are we downscaling, Switzerland and not Namibia? And if we need to downscale Namibia and we need to downscale Switzerland, why are we even downscaling? Why don't we just do this together globally and engage the Namibians? And so Eve is really trying to create a platform where we can work together to engage and inform the world about the changes coming. The idea of Eve is here in this diagram right now, is that we would bring together a few regional engines, super regional centers, which would run and access these computing facilities, forefront tier 0 computing facilities. So each one of these engines on the bottom are filling a data layer, which is then open to everyone to explore. And so each one of these engines we envision as a ECMWF scale operation with a couple hundred people connected to exascale computing facility, creating a data layer that is open for people to learn from, to access directly. And by doing this in a way that involves the stakeholders from the very beginning, you can also allow not people just to surf on top of the data, but to actually go back into the data layer and to go back into the engine. So having a user-driven system. So instead of the knowledge industry where the academics, people like me, push our knowledge on users, we try to create a system with users that makes the information visible to them. So this is what Eve is trying to do, this 3-layer system of engines, data, and information, engage multi-sectorial stakeholders. And I think in doing this, we'll see it will create new economies of weather and climate, will stimulate research and technology in ways that we can't imagine, and will open all sorts of opportunities for new people to engage in the field. And so with that, it's my final slide here, is that we imagined Eve as a digital infrastructure that applies the latest advances in science and technology to create and disseminate climate information that is as useful as possible to as many as possible. And to do that, we have to do it together. We need access to the most performant computing systems, and we need to bring together AI to help us understand what the data is saying that we're creating. In Flesh and Stone, we imagine 3 to 5 of these centers, each one of them sort of a 30 megawatt facility, and a funding volume of about 300 million euro per year per center, which is really, quite frankly, a pittance if we think about the types of changes that we're talking about. So you take climate change seriously, or you don't, but you can't take it seriously and be worried about that number at the same time. Thanks very much.